Welcome to the Nice Future Climate Scale Solutions with Nuclear Produced Hydrogen Global Perspectives on Progress webinar. I'm going to quickly go over a couple logistical items before we get started. All attendees are in listen-only mode. This meeting is being recorded and will be available for replay on the Nice Future website. I can put this URL in the chat for everyone. Closed captioning has been enabled for this webinar, and you can choose to turn subtitles on if you wish. If you have any technical issues during the webinar, please use the raise your hand feature and I'll respond to you directly over chat. There will be a brief Q&A session after each speaker. During the presentation, please feel free to submit questions through the Q&A button on the bottom of your screen. And now I'll pass it over to today's moderator, Shannon Bragg-Sitton.
Welcome. My name is Shannon Bragg-Sitton, and it is an honor to introduce our speakers and participants today in this webinar. I'm a Division Director for Integrated Energy and Storage Systems at Idaho National Laboratory in the United States, and I also serve as a National Technical Director for the U.S. Department of Energy Office of Nuclear Energy Program on Integrated Energy Systems. I'm here today representing the Clean Energy Ministerial's Nuclear Innovation Clean Energy Future, or NICE Future Initiative. In a moment, you will hear from my co-moderator, Dr. Sunita Satyapal, who leads one of our sister programs in DOE under the Office of Energy Efficiency and Renewable Energy, and she is also representing the Clean Energy Ministerial's Hydrogen Initiative. Thank you to these two key clean energy ministerial work streams for bringing us today's program. Also, thank you to the energetic staff for hosting the webinar, and to Julia Visconti and John Michael Murray of the NICE Future team for their work to organize this event. We also want to thank our supporting organizations, the International Youth Nuclear Congress, IYNC, and the North American Young Generation in Nuclear, or NAYGN, and invite you to visit their websites to learn more about all the great work that they do. Today, we have more than 275 registrants from around the world for this webinar, and we hope that you and your colleagues will join us for other webinars in this series on cutting-edge topics, and also sign up to receive our announcements on the nicefuture.org website. Today's webinar is one of the activities in preparation for the next Clean Energy Ministerial, which will be CEM 13, held in the United States, specifically in Pittsburgh, Pennsylvania, from September 21st through 23rd of 2022. CEM 13 will be hosted by the U.S. Department of Energy's Secretary Granholm, and it will be a great opportunity to put nuclear energy's innovations at the center of our clean energy plans and actions. Briefly, let me say a word about NICE Future, as my colleague Sunita will further mention the Hydrogen Initiative. NICE Future is led by the US, Canada, and Japan, with 10 other participant countries and 17 partner organizations to explore the potential for nuclear energy uses, innovations, and greater systems integration to accelerate progress toward clean energy goals. The initiative recognizes that there is no single solution to clean energy, and we foster collaboration among a number of clean energy supporters to explore diverse solutions. This webinar today is focused on the use of nuclear energy to produce hydrogen without emitting carbon dioxide. Clean hydrogen production is being pursued in many countries due to its versatility as a clean energy carrier. The combination of nuclear energy and hydrogen offers a significant promise as a climate change solution. In the United States, nuclear energy operating on the grid today provides us about 20% of our nation's electricity and about half of our non-emitting electricity. The fleet of 94 nuclear reactors is a workhorse for clean, safe, reliable, and firm generation capacity. And over the last 25 years of operation, this fleet of reactors has reduced CO2 emissions in the US by 16 billion metric tons. But today, that fleet only provides us electricity to support grid demand. In the US and in many countries represented in the panel today, we have been rethinking how we can use our current clean energy generators to do more than just put electrons on the grid. We are working to design and deploy new systems that will allow continued provision of electricity, but will go a step further to also provide heat and steam to support other energy demands, thereby providing an avenue for decarbonization of industry and transportation in addition to the electric grid. Demonstrating these non-grid applications of our current fleet of nuclear reactors will lay the groundwork for greenfield installation of advanced reactors as well, where these advanced nuclear technologies can offer enhanced efficiencies, greater fuel utilization, and significantly longer fuel cycles than our current fleet plants. And many also reduce or even eliminate water use through adoption of advanced thermodynamic cycles. Many of these systems are being designed to support industrial applications, hydrogen production, which we'll speak to today, as well as synthetic fuels. And they will be available at a variety of scales, ranging from megawatt scale microreactors, hundreds of megawatts from small modular reactors, and large gigawatt scale systems in order to support the energy needs ranging from remote, islanded locations to the traditional centralized grid. In today's discussion, we will provide some exciting insights about this new thrust in national investments in hydrogen production. And in some cases, these are multi-billion-dollar investments. We'll hear about research and development activities from some key countries representing key national research programs, including insights into what policies and innovation breakthroughs we will need for hydrogen to be deployed at a massive scale around the world. These developments are new, rapidly evolving, and they could be paradigm shifting in how we approach energy system solutions. We hope that today's discussion will provide policymakers with important insights from this worldwide experience. As we go through today, we have asked each speaker to give a presentation of about 10 minutes. And following each presentation, we will have a question and answer session for that speaker. If there is time, we will continue with a roundtable discussion at the end of the webinar as well. Please use the Q&A function in Zoom in order to post your questions for each of those speakers as we go through the webinar itself. Now I'd like to turn the microphone over to my co-moderator, Dr. Sunita Satyapal.
Thank you very much, Shannon. And it's great to have this webinar. And thank you also to all of the co-organizers, and welcome. What I would like to do now is give some opening remarks, both on behalf of the SEM Hydrogen Initiative and the U.S. Department of Energy's Hydrogen Program. And SEM, the H2I, was launched by Canada in 2019. And the co-chairs include the US, the European Commission, Japan, and the Netherlands, and about 25 countries focused on accelerating progress, particularly in the deployment side for hydrogen technologies. And we also coordinate across other international initiatives, Mission Innovation, IPHE, the International Partnership for Hydrogen and Fuel Cells in the Economy, IEA. There are a significant number of international partnerships on hydrogen, and SEM has launched key global initiatives such as the Global Ports Coalition, also the H2 Twin Cities program, to really help accelerate deployments and partnerships, collaboration specifically in hydrogen. So if we go to the next slide, I'll give an overview of the US Department of Energy's activities. And first of all, hydrogen is one part of a very broad portfolio of activities. We have a hydrogen program plan available online, and it covers really the entire value chain and all the resources. Today, we'll be focusing on nuclear, but we're also looking at renewables, fossil or waste with CCS, and covers basic science all the way up to deployments. And again, from production, delivery, storage to end use. We have over 400 projects, and DOE is the main funding agency, federal agency in the US focused on energy. And we fund currently 400 active projects, over 200 companies, universities, about 15 national labs, including the Idaho National Lab, which is the lead national laboratory for nuclear. And as Shannon mentioned. But our three main priorities are really, we have to get to low cost hydrogen. So I'll talk about our main initiative there. We also need low cost and obviously safe and efficient infrastructure, both delivery and storage. And then the third priority is enabling end use applications at scale. So that's really our main focus. And that includes workforce development, safety codes and standards, our environmental justice priorities. So in the US, we have the administration priorities in addition to net zero by 2050, a clean grid by 2035, an initiative called Justice 40, where 40% of our federal benefits would impact disadvantaged communities and those who've historically experienced environmental injustice. And so the H2 at Scale initiative is our key focus, which really depicts the Swiss Army knife perspective of hydrogen. So you can see the versatility, the fact we can use all the resources on the left. And today we have the conventional gas grid shown in gray and the red conventional electric grid, but you can also bypass those and produce hydrogen and then use it for multiple end use applications. So either for power back to the grid or fuel or feedstock. So it really represents that versatility, the flexibility, and providing different options for hydrogen. But our focus is really hard to decarbonize sectors. So first, industrial applications such as steel alone accounts for over 7% of global emissions, ammonia, other examples, chemical fuels, transportation, especially heavy duty transport, and then power and energy storage. And here from the US perspective, with our administration goal of a completely clean grid by 2035, as we see renewables increase, we'll have greater need for long duration storage. And if we click once more, from a US perspective, we already produce about 10 million metric tons of hydrogen per year. And we see scenarios for significantly more. And to give you an example, if we produced another 10 million, that would basically require doubling today's solar or wind deployment. So there's huge opportunity for nuclear to hydrogen. And if we go to the next slide, if you ask where are we today in the US, we actually have thousands of fuel cells, multiple applications as shown on the left, niche markets such as over 50,000 forklifts operating in major distribution warehouses. So Amazon, Walmart, major companies for completely zero emissions, over 115 hydrogen stations just for the fuel cell market. That's really helped to incentivize the market, build up the infrastructure, backup power, thousands of fuel cells for cell phone towers, stationary power, over 12,000 commercial vehicles, mostly in California, about 50 stations, buses. And the top map shows that most regions have natural gas to hydrogen. Some flagship projects there. And the bottom map shows examples of PEMs, or proton exchange membrane electrolyzer installations. This is continuously changing. This is the version we posted from June of last year. We'll be updating this, but you can see over 170 megawatts. And we also have over 1,600 miles of hydrogen dedicated pipeline in the US, about 3 geological caverns, including the world's largest in Texas. So we see this growing infrastructure in this nascent market. But if we go to the next slide, I wanted to emphasize the nuclear projects. And so we're really excited, both my office and the Office of Nuclear Energy at DOE co-funding 5 projects now, very recently announced, specifically for nuclear to hydrogen. So these will be coming online in the next few years. And you can see the geographical variation here. So the specific plants, Ohio, New York, and others, so around the country, and we'll be using electrolysis and producing hydrogen. And basically, these will be first of a kind demonstrations. So understanding the dynamic response, being able to provide that hydrogen for other applications, And we have also not just low temperature or PEM electrolyzers, but we'll be integrating, in fact, at Idaho National Lab at Shannon's laboratory, the largest in the country, 250 kilowatts of a high temperature solid oxide electrolyzer with thermal sources. Again, looking at the broad portfolio of both low temperature, relatively near-term deployments, and then integrated with high temperature for improved efficiency, nuclear to hydrogen. And so the next slide will summarize the key initiative here that I want to emphasize, which is the hydrogen shots. We had, in response to President Biden's request last year at the climate summit to our Secretary of Energy of how can we really accelerate our progress. And this is similar to the moonshot that the US had over half a century ago with John F. Kennedy. And so there'll be a series of energy Earth shots. And the very first was the hydrogen shot, which is a bold, ambitious target of 111, so $1 for 1 kilogram of clean hydrogen in 1 decade. That is the shot. And so we have all hands on deck to achieve that goal within a decade. And if we go to the next slide, we have had a summit, and all this information is available online. We had thousands of participants, our Secretary John Kerry, Bill Gates, many CEOs from companies, congressional members. And we have, if you look at the feedback that we got from stakeholders, you can see the yellow bar, cost is the high priority. But you can also see many other hydrogen. Again, we're at such a critical time. I've been in this field for many decades, but infrastructure, policy, R&D, awareness. And so with all of those challenges and needs, if we go to the next slide, I wanted to highlight the most recent announcements in the US with the Bipartisan Infrastructure Law, or Infrastructure Investment and Jobs Act. And this provides $9.5 billion for clean hydrogen, including $1.5 billion both for electrolysis, that's $1 billion, and then $500 million for clean hydrogen manufacturing and recycling. So we'll start with the end of life in mind. So whether it's catalysts or other components, so designed for recyclability and sustainability. And then $8 billion specifically for at least 4 regional clean hydrogen hubs. So similar to the H2@Scale concept, how do we co-locate production with end use? And nuclear, renewables, and fossil are part of the statute of the legislation for the hubs. And then we also have specific in the legislation goal of $2 per kilogram by 2026. And then developing a national clean hydrogen strategy and clean hydrogen standard. So finally, I think the last slide is the importance of resources. So again, a big thank you to all the organizers for this webinar. This is a very quickly moving field, so feel free to stay tuned. We have an Increase Your H2IQ webinars, newsletters, a Center for Hydrogen Safety, over 70 global members and partners, industry, the Hydrogen Council, providing training material and accreditation, incidents and best practices. And then June 6th to 8th, we have our virtual hydrogen, DOE-wide hydrogen program review. We'll present our hundreds of projects. We typically get a couple of thousand people, and then a hydrogen day in the US to increase awareness. On 1.008 is the atomic weight of hydrogen. So October 8th is designated in the US as National Hydrogen Day, where again, we spread the word. Public awareness is one of the challenges. And so please do feel free to sign up for any of our resource information. So with that, I'll turn it back to Shannon, and have a good conference to everyone. Thank you.
Thank you so much, Sunita, for giving us that excellent framing of this session. Sunita does not have time to stay for some of the questions and answers. I do see one question pop up. Sunita, would you have a chance to spend 1 minute with us and answer one question?
Sure. Yes, I should mention that we, in terms of the hydrogen hubs, if you look on our website, we launched a public request for information, which just closed a couple of days ago. So we have a lot of information in that RFI. So we actually outlined the funding opportunity strategy and how we actually plan to implement. So please take a look at the website, but we're still formulating the plans, and we'll be sharing the plans publicly before we officially, issue the funding opportunity announcement.
Thank you, Sunita. Yeah, the question was if there are any particular considerations given to nuclear power in selecting hydrogen hubs. And it sounds like, things are still in formulation. I don't know if you want to add anything quickly.
Yeah, it definitely says that we need to consider at least one nuclear to hydrogen project. So I think there's tremendous opportunity there.
Absolutely. Well, thank you, Sunita. I'm sorry you weren't able to stay for the whole session, but we will go ahead now and move into our panel of speakers, starting with Dr. Sama Bilbao-y-Leon. Keeping the desire for rapid deployment in order to address the urgency of the climate challenge in mind, it is very fitting for us to hear from the World Nuclear Association about perspectives on the global use and commercialization of these technologies. So our first speaker is the Director General of the World Nuclear Association, Dr. Sama Bilbao-y-Leon. Sama is a nuclear engineer and a tireless advocate for sustainable energy. She has a very diverse professional experience, having had the opportunity to contribute to the advancement of nuclear science and technology through her work, first in the nuclear industry at Dominion Energy in the US, and then in academia at the Virginia Commonwealth University, also in the US. She then moved to international opportunities, working at the International Atomic Energy Agency, at the OECD Nuclear Energy Agency, and then with Generation 4 International Forum before moving to the World Nuclear Association. So in her talk this morning, Sama will provide an overview of some of the global initiatives using nuclear energy for hydrogen production, with an emphasis on the United Nations Energy Commission for Europe, UNECE toolkit for policymakers to attain carbon neutrality, which includes nuclear energy and hydrogen. Sama, over to you.
Thank you very much, Shannon, and thank you, Nice Future, for the opportunity to be here. So if you go to the next slide, please. So I just wanted to, for some of you that are not very familiar with World Nuclear Association, we are actually one of the partner organizations for Nice Future, and we are always delighted to contribute and to work together with all the different governments and different organizations that contribute to this work. So I'm not going to itemize this for you, but World Nuclear Association represents the global nuclear industry. More than 190 members in 44 countries in all continents are representing the entire nuclear fuel cycle. We work with the industry, we support the industry, and we represent the industry in all the international fora that discuss the different aspects of nuclear. We also inform and communicate on nuclear energy. We train the leaders of tomorrow through the World Nuclear University. And finally, last but not least, we really are working very hard to engage in the global energy debate so that nuclear energy has a seat at the table. So I'd like to go to the next slide, because in our opinion, of course, and I think maybe in many of your opinion, nuclear energy does offer a golden opportunity to build a cleaner, more equitable world in which everybody has access to clean, abundant, affordable energy and a high quality of life. And one of the things that we like to emphasize when we communicate and when we talk about the role of nuclear energy at a global level is something that Shannon already mentioned, which is the very important role that nuclear energy has beyond electricity. So for example, in using zero carbon nuclear heat for industrial applications, for hydrogen generation, for transport, for shipping, for district heating, etc., etc. So today, I am going to focus a little bit on one of the projects in which we have been collaborating, which is the UNEC, the United Nations Economic Commission for Europe. They have developed a toolkit for policymakers to attain carbon neutrality. So this toolkit is meant to help policymakers to make informed decisions on how their nations can accelerate the energy transition towards attaining carbon neutrality. And maybe for some of you that may not remember who are the countries that integrate the United Nations Economic Commission for Europe, I will remind you that it does cover more than 47 million square kilometers all over the world, actually. So it includes the countries in Europe, of course, but also countries in North America, such as Canada and the United States, and also in Central Asia, such as Kazakhstan, Kyrgyzstan, Tajikistan, Turkmenistan, Uzbekistan, and also in Western Asia, such as Israel. So even though the name may indicate you that is a very European focused organization, I think that this gives you the vision that we are really talking to a very, very large number of the countries in the world. So we think that this toolkit for policymakers to attain carbon neutrality is incredibly important because I don't have to tell you that improving energy efficiency and decarbonizing the energy supply are essential, not only to meet the Paris Agreement targets, but also to ensure that everybody in the world achieves the sustainable development goals that we all need to achieve. So in this particular toolkit, the UNEC is actually focusing in nuclear energy, renewable energy, highly efficient fossil fuels with carbon capture, use and storage. And of course, hydrogen, as you see in this slide, is a key component to this. So the idea here is to decarbonize the entire energy system through a very rapid transition from where we are today, fossil fuels or a high concentration of the use of fossil fuels, to low and zero carbon technologies. So what we are trying to do, or what the UNEC is trying to do with this toolkit, is to decrease the traditional use of fossil fuels by increasing the use of renewables, nuclear power, hydrogen, and CCUS. So all these things can be done in an interplay that I like you to see in this slide, which is very important to realize that all these technologies are going to be necessary to have an optimized and reliable system. And you see here how they really work together. And then one thing that is very important, it is absolutely essential for attaining these carbon neutrality energy systems of the future. We really need to look at this as an integrated systems approach, and we need to really work together to put in place the financial, the technical, the policy capabilities that are going to allow all these countries to build the needed infrastructure and access to the different natural resources sustainability. So if we go to the next slide, I'll give you a very brief peek on one of the items, one of the pieces of the toolkit, which is the UNEC Nuclear Power Technology Brief. So this is a brief, very, very short. You can access it in the UNEC website, that gives you a very comprehensive overview how nuclear energy can be or is an important source of low carbon electricity and heat. So I won't go into the details, but because in fact, one of the things that I want to highlight here is the role of hydrogen. One thing that I would like to highlight though is this brief does emphasize that in order to achieve this energy transition, we are going to need large-scale nuclear power plants. We are going to need also small modular reactors and advanced reactors that are using different technologies, as well as micro reactors that they all have their different optimum applications, and they all have an important role to play. So if we go to the next slide, I'd like to show you another very important document that is part of this toolkit, which is the report on life cycle assessment of energy sources. This is a definitive study that looks not only at the environmental footprint from different energy sources, but also at the health impacts and the system on impacts on ecosystems. So this is probably maybe not super big, but I think that you can see there, this particular graphic shows you the greenhouse gas emission footprint of the different energy sources. And you can see something that many of you already knew, how nuclear has one of the smallest footprints. But of course, that is also true when we are talking to human health. Nuclear power shows very low impacts in global human health. And also when we are talking about ecosystems, very low impacts in the overall ecosystem damage indicator. So if we go to the next slide, I'll go a little bit more in depth into the brief that has been developed for hydrogen. So there is a specific brief that focuses in hydrogen, and number one looks at the sustainable hydrogen value chain. So this is very important because not only need to identify all the different low carbon sources that are going to be used to produce this low carbon hydrogen that is going to be a very important energy carrier in the energy systems of the future. But we really need to put in place the entire value chain, the entire infrastructure in order to make that to happen. So very quickly, a handful of takeaways. So first of all, as I mentioned, we need to make sure that we diversify the risk and we promote all sustainable hydrogen technologies. And very important, make sure that build on existing natural gas infrastructure to reduce the distribution cost and promote the trade. And of course, we continue to work on the improvement of the electrolyzers. So we are trying to accelerate the deployment and the technology that we are using to electrolyzers. Also very important is the development of clear regulatory frameworks that are going to be supportive of all these different low carbon technologies that are going to be available to produce sustainable hydrogen. And then finally, it is very important to promote the projects in a way that are going to create capacity locally and regionally where these new technologies, these clean energy systems of the future are being deployed. So let me go to the next slide, in which you see a brief infographic that is extracted from the technology brief on hydrogen, where it is a very, I think, quite clear diagram that shows the different energy sources that we are currently using, that we will need to use in the future in order to ensure the production of sustainable hydrogen. And of course, I don't have to tell you that nuclear energy is one of the key energy sources that is going to be able to achieve that. So let me finalize very quickly, Shannon. If we go to the next slide, in addition to these documents that I have also mentioned that are available already on the website, I want to highlight that the UNEC is working on a project on sustainable hydrogen production pathways. And the project is really working on the premise that hydrogen could transmit up to 24% of the world energy by 2050. And in fact, this project is particularly aimed to help countries in Eastern Europe and Central Asia to develop their national hydrogen action plans and to accelerate any needed action. So I'm not going to walk you through the different phases, but I think that is a very solid project that I think, as many of the other activities in the UNEC, is an excellent opportunity to develop capabilities and to move forward in this clean energy transition. Then my very last slide, if you go to the next slide, I won't itemize this for you, but the next one, please. You can see that there are already, and we will hear about this today in the rest of the speakers, and we are working with many of these stakeholders. Hydrogen, it is going to be a key component of the low carbon energy transition. And you see how many countries in all continents are already doing a lot of work in order to ensure that hydrogen can be used, and more importantly, or just as importantly in our case, that nuclear energy is a key component of the technologies that can ensure this sustainable hydrogen production in an affordable manner. So I'll stop here. Let's go. I mean, you can go to the last slide, but with this stop, I'm back to you, Shannon.
Thank you so much, Sama. That sounds really exciting. It's nice to see some of these collaborative efforts globally. What would you say is the unique value of this UNECE toolkit, specifically to policymakers?
Yes. Well, I think that, well, first of all, it comes from the UNECE, so that already comes with a very strong pedigree. As you know, all UN organizations, they are very interactive with all the member states. So we are bringing in, so first of all, we are making sure that it's going to reach the right people at the government levels in a very large number of countries, as you saw before, because obviously the UNECE is a very large part of the world. But I think that what is more important is the way this toolkit has been developed. And because we have been collaborating a little bit behind the scenes, I can tell you that it's been incredibly exciting to see the strong engagement that the UNECE has had with all these low carbon technologies, making sure that they truly understood the different aspects of the technology, truly understood what was needed for countries to be able to deploy these different technologies as needed if they chose to do so, and to provide the information and to help them align the resources, human and otherwise, and to put in place the infrastructures to achieve the goals that they are looking. So it is a very comprehensive, very hands-on, very practical project that we are seeing already how many countries are being able to make the most of it.
Thank you, Sama. Let me ask just one quick additional question. What do you think is the most significant barrier to getting hydrogen from nuclear energy deployed on a massive scale?
Well, I think it's not so much the hydrogen part. I mean, I think that there is going to be there's a lot of work that you guys are doing already at Idaho National Laboratory and many other places in the world to actually make that connection. I think that there is a lot of hopes and expectations of the role that nuclear energy can and should have in the overall decarbonization, whether it's for hydrogen or for something else. So I really think that this is the problem here, not the problem, but the challenge, I think, for the global nuclear enterprise is to really ramp up fast enough to actually address the needs that we are going to have. I mean, we really need to, if we really want to provide not only the electricity that is needed, but also this hydrogen or the industrial heat or fresh water, etc. We need to put in place not only the financing, we need to put in place the policy making, basically the policymakers, governments need to put in place the strong statements giving confidence not only to the nuclear sector, but also to the finance community. And finally, well, we just need to actually start doing what we know we can do, because it's been done in the past, in the 90s and in the 80s.
Thank you so much for those insightful remarks. I appreciate your time today. We're going to go ahead and move to our next speaker, Mohammed Al-Breiki, who has been the Director for Strategy, Program Management, and Excellence at the Emirates Nuclear Energy Corporation, ENEC, since 2017, after first joining ENEC in 2011. Mr. Al-Breiki is responsible for the development and implementation of strategies aligned with ENEC's vision to power the growth of the United Arab Emirates, become a global leader in nuclear energy, and build a sustainable nuclear infrastructure in the UAE. He also leads the development and performance measurement of ENEC's 5-year strategic plan. Today, we will hear about the UAE's Barakah nuclear energy plant, which is the first of its kind in the Arab world, and the only multi-unit operational nuclear plant in the region. This makes the UAE a pioneer in the development of clean energy technology in that region. And the Barakah plant is leading the largest decarbonization effort of any industry in the UAE, creating numerous opportunities for expansion into research and development of other technologies, such as the production of hydrogen for economy-wide decarbonization. This presentation will look at the challenges and opportunities that this nuclear energy development has brought to the UAE for production of hydrogen. So with that, Mr. Al-Braiky, I look forward to your remarks.
Thank you, Shannon. And hello, everyone. It is a pleasure to join you here today. And thank you for the Clean Energy Ministerial Nice Future Initiative for organizing this webinar on such an important topic for the future of sustainable development and decarbonization. If we go to the next slide, as you can see, we all recognize that the world is facing an enormous challenge in the face of rising emissions and climate change. In developed economies, this is looked at from the perspective of reducing emissions. At the same time, growing economies like the UAE need an increasing amount of energy to power that economic growth. Generating the electricity needed to ensure sustained economic growth is one aspect, but at the same time is compounded challenge by the need to do this using clean energy technologies. If we go to the next slide, we'll see the UAE's energy strategy 2050. We clearly see the vision of our nation, where we project 6% growth in energy demand every single year, which is more than 3 times the global average. At the same time, we aim to generate 50% of our electricity from clean sources, resulting in a 70% reduction in emissions from energy generation. In fact, the UAE was the first country in the region to commit to achieving net zero emissions by 2050 for electricity production. The only way we can do this is by using a combination of reliable, zero carbon nuclear energy and renewables, especially when it comes to solar power. But to decarbonize other sectors, we would need low carbon alternatives like hydrogen. At the next slide, I'd like to shed some light on the UAE's pathway to net zero. The net zero is powered by over 11 integrated programs in 4 priority sectors, outlined in the federal decree published by UAE Cabinet in June last year. We could see most notably here the sustainable energy mix, which we have includes the nuclear energy development. The Barakah plant is already leading the largest decarbonization effort in the UAE and will reduce the nation's carbon emissions by 22.4 million tons every year. That is like taking 4.8 million cars from the roads annually. Additionally, we see the need for hydrogen as a future energy source in industry, energy, and transportation. This is where we stand today with our nuclear energy program. Barakah Unit 1, the far unit at the right here, as you can see at the slide, it is a single largest generator of electricity in the country today. Since it began operating almost a year ago, it has generated more than 10 terawatt hours of electricity and prevented about 4.5 million tons of CO2. That's enough power for 150,000 Emirati homes 24/7 for a whole year. And that's just from one plant, one unit of the 4 units we're doing. Next to it, you see Unit 2 that is connected to the grid, and it is almost ready to declare commercial operations. Once it does, it will double the power production and the benefits that Barakah brings to the UAE. Unit 3, we completed the construction last year, and the coming months we'll ready the startup with the coming months. At the same time, in Unit 4, expected to complete construction later this year. Once the 4 plants are fully operational, the plants will deliver up to 25% of the nation's electricity with zero carbon emissions. Next slide. Thank you. However, having the 4 plants fully operational, the plant has a much bigger potential than just electricity generation. Many existing light water reactors plants, as we heard from Dr. Sunita and Sama, they're beginning in integrating electrolysis equipment at their plants to cleanly and affordably meet their own hydrogen demand. An early opportunity for ENIC is to install electrolysis at Baraka plants and establish a leading edge in technology capability. The 4 units of the plant have the potential of generating up to 1 million tons of hydrogen per year. This clean fuel can be used in many, many sectors, including heating, transportation, manufacturing, and others. In this way, the Baraka plant can help decarbonize not just electricity generation, but also the other energy-related emissions that contribute to climate change. Today, the UAE is in a unique position when it comes to existing infrastructure, because it's a premier producer, as you know, with the top-of-the-line storage and transportation capabilities of liquid fuels. I'd like to conclude with this slide that the UAE is a regional and pioneer in many, many aspects. The Baraka plant is the first nuclear energy plant in Arab world, making us the regional leader in developing the knowledge, expertise, and skills needed to safely operate a nuclear plant. Now we're looking at ways and opportunities, potentials to apply our expertise and know-how into becoming a regional leader in nuclear-produced hydrogen. In addition to the benefits this has for decarbonizing the economy, it also presents us with opportunities to lead on the development and deployment of new technologies, such as high temperature electrolysis, also opening up opportunities in research and development. As Dr. Sunita mentioned, the possibilities are endless, and the opportunity is big. But when it comes to nuclear science and technology, and especially the UAE is clearly leading the way in decarbonization and sustainable development. With that, thank you very much, and I will wait for any questions that you might have.
Thank you so much for those remarks. Your presentation makes it quite clear that the UAE is a pioneer in your region, and there's also great potential for additional technology in your region. So as you think about that, what do you see as the primary challenges for hydrogen production from nuclear energy as you move forward?
The challenges right now, as we could see from what we heard or learned from Dr. Sunita and Sama, the technology to produce hydrogen is there. Mm-hmm. And the cost is going to become coming down, but we also need to think about from a challenge when it comes to the supply chain throughout the production of hydrogen and coupling it with nuclear. That would include transforming or the transport when it comes to the hydrogen. Once we produce the hydrogen, we need to distribute it. For that, you need to form some partnerships with other organizations and utilize the existing infrastructure that we have. So from that aspect, we need to study it throughout and align with the right partnerships that we have to make it happen.
Thank you. And where do you see the demand for hydrogen? What are the hydrogen markets you are specifically looking at in the Arab world?
Yes, and as I mentioned last year, the UAE was the first in the region to commit to achieving the net zero by 2050. Several other countries followed course after that. Hydrogen as a zero carbon fuel will help decarbonize a lot of sectors. It will help and currently that are currently hard to decarbonize. We're talking transportation, industry, heating, and many, many others. So the prospects of hydrogen market within the UAE and the Arab world, I think they're very, very huge.
Thank you. And one additional question, are there any plans to build additional nuclear units or power stations in the UAE at present?
We're currently studying the thing about the expansion, but it's currently in the study phase right now, I would call it. We're quite busy, as you see from the 4 plants, and we hopefully wanted to deliver that first, inshallah.
Great. Well, thank you, and appreciate your comments and your pioneering this area in your region. We'll go
Thank
ahead
you.
and move to our next speaker, and for that, we will turn to Latin America, where there are exciting developments going on in Brazil. For that, we will hear from Dr. Giovanni Machado, an economist who holds a doctorate in energy planning. He is currently the Director for Energy Economics and Environmental Studies in the Energy Research Office, EPE, in Brazil. Giovanni will cover the development of a low carbon hydrogen economy in Brazil and the role of nuclear energy in the energy transition. Particularly, he will point out the nuclear hydrogen nexus in Brazil. Giovanni?
Hello, everyone. Thank you so much for the invitation and the opportunity to have this talk on behalf of the Brazilian government. I also would like to congratulate the organizers for such an important event and my colleagues of the webinar for providing a lot of food for thoughts. Next slide, please. EPE, the Energy Research Office, is a governmental body for energy planning studies, supporting the Ministry of Mines and Energy in decision-making process in Brazil. For international reference to understand EPE, it's just to look the kind of relationship Energy Information Administration and DOE has in the US. That's the kind of relationship EPE has with the Ministry of Mines and Energy in Brazil. Next slide, please. Well, in our view, nuclear energy will have a key role in the energy transition because it provides energy security, system reliability, decarbonization, market coupling with different sectors and spillovers. Particularly, nuclear will have an important role in the hydrogen economy, and there are different technological routes to achieve to produce hydrogen from nuclear. And we understand it's very important to take advantage of all technological routes. Next slide, please. Well, I will not take long in this slide. It's just general figures in Brazil regarding nuclear infrastructure. But it's important to bear in mind that as of today, nuclear has as installed capacity barely 2 gigawatts of installed capacity, and we are in the next 10 years basically double the installed capacity. Next, please. In the long term energy planning, as we call the National Energy Plan 2050, we consider nuclear and more important that have the figures for expansion from 8 gigawatts to 10 gigawatts by 2050. The more important issue is to consider also new technologies and improvements and innovations in nuclear industry. Particularly, we see the SMRs as a very promising innovation in nuclear, and with the possibility to coupling with the hydrogen production in a decentralized strategy to take more advantage of the modularity all over the country. Next, please. It's important to say that nuclear is not only in energy planning in Brazil, but it's a real thing. It's going back, and there is a lot of pieces of legislations and regulations to promote new investments in nuclear in Brazil. Next, please. Going to hydrogen, it's very important to say that government support in R&D and innovation is not new in Brazil to hydrogen. So there is a long-term commitment to hydrogen, and this commitment brought some results already. So I'm not talking only about programs, plans, white papers, and resolutions for the National Council for Energy Policy in Brazil, but mainly all the market and technological and human results that this commitment brought already. So I'm talking about capacity building, both institutional and technological and human capital formation. It's very important. There is a lot of different projects, different parts of the value chain of hydrogen, and a lot of universities and research centers and industries associated to those efforts. And more important, there is already in Brazil some startups related to hydrogen along the value chain. Next, please. Recently, we released the Brazilian National Hydrogen Program, the PNA2, and it started with a resolution of the CNPE in last April 2021, and it covers different aspects of the hydrogen economy, going from technological aspects to training in capacity building, energy plan, legal and regulatory framework, and market growth and competitiveness, and also, of course, international cooperation. Next, please. We have a technological agnostic approach. We focus on low carbon hydrogen. It's very similar approach to at scale initiative presented today by our colleague from DOE. Next, please. Probably this is one of the most important issues in my presentation, just to make clear that hydrogen production from nuclear in Brazil is already there. So as of today, we produce already some hydrogen as a byproduct from the process to have sodium hypochlorite from seawater based on electrolysis, but because of the concentration, it's not, it's still 96% of pure A2, so it's not placed in the market already. By the opposite, it's vented to the atmosphere. But there is already a pre-feasibility study, and the project shows that it's cost effective to invest in a purified unit, so you can enhance the concentration to 99% of purity. And the payback is less than 2 years. So we understand that this project, when detailed, will go ahead. Next slide, please. So just to conclude my presentation and to wrap up it, some key message. So we see that nuclear role, there is a nuclear role in the energy transition basically related to energy security, system reliability, decarbonization, and spillovers, technological spillovers, and the possibility to coupling with other markets, not only carbon market, but also industrial market, particularly for supplying heat, and hydrogen. There is a lot of things going on in Brazil, and particularly we see SMR bringing new opportunities to nuclear industry in Brazil, particularly related to hydrogen. And we see the nuclear hydrogen nexus as something to improve the economics of both. But of course, as in everything related to nuclear, engagement and communication still matter for having that. So that's all I have for today. I leave back to Shannon. Thank you so much.
Thank you, Giovanni. It's very clear that Brazil has a commitment to hydrogen, and I really appreciate seeing the technology agnostic approach. Given that, what is the position of the Brazilian government on the role of nuclear energy in producing hydrogen?
Yes, as we do have this technological agnostic approach with the focus on low carbon hydrogen, we understand that nuclear has a role to play in the hydrogen production, even while we are already producing some. So it's a matter of purification and to get the right concentration of hydrogen. And of course, nuclear brings energy security, system reliability, and contribute to the decarbonization of the economy. So we see it's very important. And just to add something, that's why we have this approach to the certification. We understand that the certification of hydrogen should be concentrated on carbon intensity rather than on technological routes, because we understand that if we link the hydrogen to the carbon market, then we will foster the development of the hydrogen economy. So we understand that this is the best way to have a larger and to accelerate the supply of low carbon hydrogen in Brazil, taking advantage of having different feedstocks all over the country, and so we could get cost advantage related to logistics and to have production all over the country, taking advantage of these different potentials and feedstocks in Brazil.
Okay, thank you. So I understand that certification really is focused on that carbon footprint associated. Do you foresee any regulatory challenges to integration of the technologies, nuclear and hydrogen, or in meeting purity requirements for the hydrogen produced?
Yes, I think most of the discussions as of today is very concentrated on the technological aspect. And of course, mainly in Brazil, renewables will have a major role in producing hydrogen. But even then, we understand that we should not leave the other technologies to produce hydrogen behind. So we have to focus on, once again, low carbon hydrogen. Doesn't matter the kind of technology you provide. The focus should be in the cost and in getting low carbon hydrogen. That's our view.
I agree with that view. Low carbon is essential to our climate solutions. Thank you so much for giving us a glimpse of what's going on in Brazil. Really exciting times. We are going to move to our next speaker now, where we turn to Japan, where there is certainly great interest in hydrogen, and we've seen some of that growth in that interest recently. It is my pleasure to introduce Dr. Nariaki Sakaba, who is the Deputy Director General at the High Temperature Gas Cooled Center within the Japan Atomic Energy Agency. Dr. Sakaba's specialty is in chemistry and nuclear energy, perfect combination for these projects. And he is also the project leader for the High Temperature Test Reactor, or HTTR, and the Hydrogen Production Project at JAEA. Dr. Sakaba, the floor is yours.
Thank you, Shannon. On behalf of the Japanese government, I appreciate Nice Future webinar for invitation. JAEA has been developing high temperature gas cooled reactor and its related technology for more than 30 years. Today, I would like to introduce our current development status concerning the HTGR and hydrogen production technology towards carbon neutrality. Next slide, please. Next slide, please. First of all, I would like to show the greenhouse gas emissions in Japan. Last year, as the Leader Summit on Climate, Japanese Prime Minister presented a plan for global warming countermeasures, that is, midterm target of 46% reduction by fiscal year 2030 compared with 2013. And 2 months after the summit, Japanese government stated the green growth strategy through achieving carbon neutrality in 2050. The left-hand graph shows the GHG emission in Japan. The emission is gradually reduced from 2013. However, 2050, additional 88 reduction is necessary. The right-hand pie chart shows the breakdown of GHG emissions in Japan. And the nuclear system will be able to contribute reduction of GHG emission from power generation, showing the orange area, 37%. HTGR can contribute beyond the power generation, such like to produce hydrogen for steel making process and fuel cell vehicle for transport, to produce steam for conventional industries, and to absorb renewable power variations. So HTGR will play or must play a dominant role to achieve the GHG reduction in the future. Next slide, please. Japan Atomic Energy Agency has been developing HTGR since 1960s. We constructed the HTTR, the only pragmatic type HTGR in operation in the world. Major specifications of the HTTR are thermal power of 30 megawatt, fuel is coated fuel particle, prismatic type, and the core material is graphite, coolant is helium, and reactor outlet coolant temperature is 950 degrees C. So the HTTR major achievements are first criticality is attained in 1998, and 50-day continuous 950 operation performed in 2010. And very recently, we carried out the station breakout test in January this year. After Fukushima Daiichi accident, new regulatory requirements were required. The progress of getting permission from NRA shows next slide. Next slide, please. This slide shows the licensing progress of the HTTR. Following the nuclear accident at TEPCO's Fukushima Daiichi accident in March 2011, revised regulatory requirements were issued by the NRA in July 2013. JAEA had submitted the application, including evaluation results, satisfying the new regulatory requirements to the NRA in 2014. Through many discussions with the NRA, in June 2020, JAEA obtained the permission by the NRA for change to reactor installation of the HTTR. HTTR has restarted its operation in 2021. It spent approximately 10 years after Fukushima Daiichi accident, but we could restart the HTTR operation again. For getting permission, the result of safety demonstration test performed before Fukushima accident was contributed. Next slide, I show the test result of safety demonstration test. In order to confirm the infinite safety features of HTGR, JAEA conducted some of safety demonstration tests. The first test was carried out in 2011. This is just before the great earthquake in Japan. The right side graph shows the results. The initial power of the HTR was 30%. The all of primary gas circulator was stopped at time 0. The core flow rate becomes 0 immediately. During the whole test time, no control load was inserted. The test results showed that the reactor is naturally shut down as soon as the core cooling flow rate to 0. The reactor and fuel temperature are kept stable long after the loss of core cooling. This is the inherent safety characteristic of HTGR itself. From the next slide, I introduce R&D for hydrogen. Hydrogen production from water utilizing nuclear energy offers one of the most attractive zero emission energy strategies to meet massive demand of hydrogen. Because of its advantage over other water-speaking hydrogen production processes using heat from HTGR, the iodine sulfur process has been selected by JAEA as an important research priority for future technologies. The IS process is composed of the 3 main chemical reactions. Please see the left side figure. The first reaction produces hydrogen, iodine, and sulfuric acid by water, sulfuric dioxide, and iodine. It is known as Bunsen reaction. But the produced acid, hydrogen, iodine, and sulfuric acid is decomposed and produces hydrogen and oxygen respectively. The reaction products SO2 and I2 are recycled and can perform a closed cycle. These reactions are endothermic reaction, and the temperature range adapts well to the sensible heat provided from helium gas in HTGR. This is a mechanism of IS process. To perform this process, our research started from beaker scale from more than 20 years ago. Now we constructed a facility that is electric heating and using engineering material. Our latest progress showed right side graph. Continuous hydrogen production, 150 hours, 30 liters per hour, was conducted with integration of all the 3 chemical reactions. JAEA developed engineering material components and confirmed the controllability of the iodine sulfur process. Experiments using hydrogen production test facility and design study on commercial system are in progress. Next slide shows the R&D for coupling technology between HTTR and hydrogen production facility. From now on, we are going to start HTTR hydrogen production test project under METI. Utilizing the actual heat generated from the HTTR, hydrogen production facility will be connected to demonstrate nuclear produced hydrogen. During the project, we will develop coupling technology between HTGR and hydrogen plant, including safety case, and to construct steam reforming hydrogen production system as downstream of the HTGR secondary helium cooling system. And we will demonstrate operability to confirm safe and stable continuous nuclear hydrogen production. And also R&D of carbon-free hydrogen production system, such like iodine saxoproheth or SOEC, will be performed in parallel. And then we will replace the steam reforming system for the next step. It is expected it will be the world's first demonstration of nuclear produced hydrogen. Next slide, please. This is the last slide. Our role of HTGR development develop key technology needed by commercial HTGR and provide R&D test beds of unique experimental computational capabilities, as well as knowledge and database to industry. Promotion of international standardization of technologies and standards through international collaborations. JAEA has experimental capabilities, computational capabilities, IPs, knowledge, databases, and can contribute to the realization of commercial system of HTGRs. Next slide, please. This is the summary of my presentations. I will skip the description. So thank you for your attention.
Thank you so much for your presentation, Sakaba-san. I'm really excited personally to see the high temperature test reactor restarted. My team has worked with your colleagues at JAEA on some of these studies related to hydrogen production, and there's really a great opportunity. How about inside Japan? Is there support for the hydrogen production and HTTR projects within your country?
Well, I have some communities, and we have the information is information. We will share the information for our status by many end users like Toyota, Honda, or the steel making process facilities, such as end users, as well as makers, Japanese industry, such like Mitsubishi Industries, Toshiba, or Hitachi, or all of the industries. We have such a community and share our progress for hydrogen production. And we are now discussing under METI to how we will proceed our development for 2050. And the Japanese government stated our HTR hydrogen production project as a green growth strategy.
Mm-hmm. And what is the public opinion regarding this hydrogen technology and a hydrogen economy potential?
Hydrogen itself in Japan is very expected because we don't have any natural gas or oil. So we have to, for the energy security, we have to make hydrogen society. But for nuclear, it is a very some of difficulties we have. So we have to make public acceptance first, but we have to develop technologies in parallel. We don't have any time for that 2050.
Yeah, we all have to move quickly on technology development, don't we? So thinking about that and this timeline that's so aggressive that we're all seeking for carbon reduction, what do you see as the potential for international collaboration on such R&D, such as the HTTR hydrogen production, and then utilization of data across different countries to help advance this technology more rapidly?
For hydrogen production technology to high temperature reactor, we have been developing iodine sulfur process, but we must study what is the best way to couple to the HTGR system. At the moment, we don't have an answer. So the best method will be selected for the next step. In that case, we need international collaboration is very important to find out what's the best way for the hydrogen production.
Yes.
And also for utilizing our database or IPs, we have the room to discuss our collaborations to outside Japan.
Well, excellent. I know I look forward to further collaboration. I think data sharing and experience sharing is very important to advancing these very needed technologies if we're going to decarbonize economy-wide. Thank you so much for your time and your remarks and an update on all of the activities at JAEA. Next, we turn to Canada with Dr. Jan Castillo, who is the head of the Hydrogen and Tritium Technologies Directorate for the Canadian Nuclear Laboratories. In this role, Jan leads the strategic direction, capability development, and execution of the research and development activities of the Directorate. Jan is an expert in deployment of innovative technologies in the areas of hydrogen production, hydrogen recombination, heavy water and tritium management, chemistry, and process engineering. And Jan is currently the task force lead for the hydrogen production processes area in the Nuclear Working Group for implementing hydrogen strategies in Canada. Jan's presentation today will cover Canada's hydrogen strategy and net zero emission targets, covering priority technologies and near-term opportunities. He will also discuss with us how the Canadian Nuclear Laboratories is supporting the strategy, especially through integration of nuclear energy with electrolysis technologies to produce low carbon intensity synthetic fuels for the transportation sector. Over to you, Jan.
Thank you very much, Shannon. I really appreciate the introduction, and also would like to thank the organizers for this exceptionally well-organized workshop, as well as on behalf of the Government of Canada. Thank you very much for the invitation to participate. So if we can go to the next slide, please. Very quickly, as Shannon indicated, Canadian Nuclear Laboratories is the national lab for Canada related to nuclear technology. It's located in Chalk River, Ontario. There was a picture of Chalk River in the previous slide. We have about in the order of about 3,000 employees, and we have operations across Canada. Clearly, our mandate is focused on national priorities and in supporting government deployment of strategic initiatives. But what it really drives us is the comparison between the picture on the left and the picture on the right on this screen, where I think all of us are aiming to really reduce global warming, find climate solutions that truly work, and develop a sustainable future. A lot of the presentation and material that will be in the next slides comes from a very recent report that CNL produced for the Canadian government on gaps and considerations for co-locating or coupling hydrogen production with a nuclear asset. So I will encourage all of you to have a look at that report. Next slide, please, Shannon. Okay, thank you very much. So it's usually a good place to start with what's the problem that we're trying to solve in teaming keeping in team with the workshop. So the key here is limiting the surface temperature increase across the world to 1.5 to 2 degrees by 2050. And obviously, we all know that this is largely driven by greenhouse gas emissions accumulating in the atmosphere. When it comes down to Canada, I'd like to point your attention to the graph on the left-hand side, where on the y-axis you have megatons of carbon dioxide equivalent, and the x-axis you have a timeline. And this is the most recent data for Canada. So as you can see, the emissions have not necessarily gone down over the last 15 years, but they have stopped increasing, and there has been economic growth. So strictly speaking, the emissions on a per capita basis, they have gone down. The target for Canada is to achieve a reduction of 40 to 45% from the levels of 2005 by 2030, and obviously to reach net zero by 2050. The table on the right-hand side, it gives you an indication of some of the larger provinces in Canada. I'd like to point your attention to Ontario, which is where the majority of the nuclear generation capacity is located. There has been a significant decrease on emission reduction from 2005 to 2019. And this reduction is largely due to shutting down of the coal-fired plants. And a lot of that extra capacity is being taken up by new nuclear reforestment projects, as well as expansion on the hydro power capacity. Next slide, please. All right, so now what do we need to get to net zero? What are the pathways and what are the critical needs? So starting on the left-hand side, in terms of pathways, to have some key bullets, we need energy efficiency, hydrogen-based economy, as all speakers have indicated before me, a large-scale electrification, obviously rely strongly on renewables such as wind and solar, and on technologies such as carbon capture, utilization, and sequestration. But some of the critical needs that are important or enables to this go through these barriers is to level the playing field. I've been hearing what are the sort of the key questions that we need to answer, and I think some of the key questions is develop a strong carbon economy, whether it's a carbon tax, carbon credits, low carbon incentives, or a combination of those mechanisms, as well as it's been lots of discussion on large scale deployment of technology, whether it's electrolysis, electrofuels, really abate the high emitting emissions industries such as cement and steel, and a large deployment of energy storage, whether it's geothermal, pump hydro, or some other combination. But an important economic point too is to mind the investment gap. It's important to recognize that as the war progresses, these assets that they were available in the past need to be protected and need to be evolved as infrastructure is developed. So, and that requires some very careful economics as well as planning. The figure on the right-hand side is the expectation as to what is the decarbonizing power of hydrogen for Canada. As you can see, there is different numbers there between the left-hand side of the screen on the y-axis. Those are associated with greenhouse gas emissions. And then what we want to get at the far end of your graph is get down to zero. So we are started at 729 megatons. Our expectation is to get to about somewhere in the order of 400 to 500. So the delta between the 729 and the 400 and 500 is the incredibly decarbonizing power of hydrogen. And that is a key part of this discussion. As is expected, that is not the only solution to get to net zero. But as you can see, hydrogen can provide about 15 to 20% of the opportunities for reducing the emissions. Next slide, please. Just like other speakers, there are many other ways to use electricity and heat to produce hydrogen derivatives as well as other products. So I will not go into this slide into a lot of detail, but what is important to recognize is if you start on the left-hand side, you have electricity and heat, especially when it comes to renewables, at low carbon intensity. And what you want to do is find ways to utilize the technology in the form of electrolyzers or in the form of thermochemical processes to convert that electricity and heat into hydrogen and oxygen. And then you have the opportunity to also connect it with carbon in the form of biomass or carbon dioxide to have a secondary set of streams that could go to a series of processes such as Haber-Bosch, alcohols production, and Fischer-Tropsch to give you ammonia, methanol, synthetic fuel, and other products. So it's important to keep in mind that we have hydrogen and hydrogen derivatives in this picture. Next slide, please. Also, keeping in mind as to how everything is coming together in Canada for the hydrogen strategy. So Canada, it has developed a series of working groups that all roll up into a strategic steering committee at the top. These working groups are all interlinked, and there is a lot of synergistic efforts and span anywhere between urban transit, hubs, vehicles, natural gas, electric cars, as well as the upcoming groups such as infrastructure, marine, ports, industrial uses. And as you can see on the bottom left side of the slide, there is a specific nuclear working group that is expected to connect nuclear and hydrogen for Canada and has been launched. So in comparison with some of the slides that Shannon went at the beginning of this workshop, Canada is a little bit behind in than the US in the deployment, but they are very quickly catching up by identifying the opportunities, the technologies, and the capabilities for the future for pilot scale demonstrations. Next slide, please. Okay, so just like any other problem, you want to start looking at where are the opportunities and where are the challenges. So very quickly, I just wanted to identify four provinces in Canada. Here is Ontario on the left-hand side, New Brunswick on the right-hand side. Everything in blue, in dark purple are high opportunities where there is industry, there is the ability to have a market demand, and the possibility of a hub for the creation of hydrogen opportunities in the future. So I will leave it at that. Let's go to the next slide. So the next slide connects Alberta and connects Saskatchewan. In Alberta, there is a large a connection with the oil industry in the area of Edmonton and the center of your slide, and Saskatchewan, when there is a large connection with also oil and gas and fertilizers. Let's go to the next slide so we can wrapping up this presentation. So as we've been hearing through the different presenters, it's important to have some specific solutions that combine all these energy, electricity, and products coming together. So what you have on the screen is an example of what we call e-scene approach, where we take in electricity and heat from a nuclear asset or a renewable asset, connected with biomass, which gives you hydrogen as well as carbon, connected with high temperature electrolysis to produce raw syngas in the right ratio to go through a Fischer-Tropsch process to produce synthetic diesel. And I think this opportunity shows that we are converting words into actions. Let's go to the next slide. Very quickly, just wanted to give you a view of what are the targets for Canada. On the left-hand side, you see at the top that Canada is already a very green grid. Most of it has hydro 60%. The production that we have for hydrogen in the center of your slide is about 4 megatons, 3 to 4 megatons. And what we will be aiming for 2050 is in the order of 20 megatons. At the bottom of your slide, and courtesy of our friends in the fuel cell world, you can see how the individual hubs are started to come up in the thinking of the Canadian industry and how they are interlinked, and they are expected to seeing a connection between the East and the West, as well as export opportunities. And we go to the last slide before we can close the presentation. Now, making Shannon's job very difficult, try to keep in on time. One last part is a big shout out on some of the modeling that has happened at Canadian nuclear laboratories and has happened in other organizations, where you want to do a hybrid energy system optimization, where you have electricity supply, different demands. And in a particular key piece of information for us is that this model can do modeling on an hourly step. So with that, I would like to thank you for your time and pass it over to Shannon. Thank you very much.
Thank you, Jan. And it's certainly a difficult task to cover the breadth of work going on in a place like Canada in just 10 minutes. So I appreciate the effort. Just a couple of questions that I want to go to. You mentioned this working group, which I think sounds really exciting. It parallels some of the work that we're doing in the US. What are the primary outcomes from the working group activities, and how will those outcomes be implemented?
Yeah, it's an excellent question, Shannon. So right now, the aim of the working groups is to first identify the questions that we need to resolve, have a common understanding, and let's say a framework that we can work from, and with the intention of have work plans from which policy and regulation, as well as other programs, could be derived. So the outcomes is to inform our government of Canada to say, for example, there are 3 or 5 opportunities in the country, and these will be the 2 in the west, 1 in the east, and 2 in center Canada. What we recommend is that you put a program of size of X number of dollars, and they begin solicitation of work in the following areas with the following technologies, and how the regulatory framework will be informed. It is associated with sort of the gaps and the opportunities and the sort of the key pieces of the puzzle that are missing to enable this transition.
Thank you. And just one additional question from our audience. You showed a couple of maps that show high potential areas for locating a hydrogen hub that could be producing significant amounts of hydrogen. As you look at those opportunities, are there any geological considerations for the placement of those potential hydrogen production hubs?
In terms of, let's say, high level storage of hydrogen, like large amounts of hydrogen
just
storage?
What makes some of those regions better than others as you look to those opportunity space? And hydrogen storage certainly would be a part of that, as well as the markets around it.
Oh, okay, I see. Yeah. Well, I think those opportunities are particularly attractive because it hits the intersection of a few combinations. There is a large industry base. There are already brown sites that they were previously used by coal-fired plants that have access to grid connections. There is ability to have a strong supply chain, and there is a demand for hydrogen and hydrogen derivatives close by. As you know, Canada, it is a very large country, so it makes sense to produce hydrogen to some extent at source on the demand centers.
Mm-hmm.
And the map that I show you for the connection of the hubs is a possibility as to how hydrogen could be piped in using the existing oil and gas pipelines. So that's the reason why those regions are particularly attractive.
Great. Just looking at your map, it does look like you also have some export markets maybe in mind as well, with some of those locations near the US. And there certainly might be some sharing across the border of these resources.
Yeah, totally. I think there are two obvious export opportunities on the one in the connection with the Great Lakes, where there is already a lot of trade between the two countries, and the connection on the east, where there is access to Europe, and Europe is considered a very large demand
Mm-hmm.
center for the future. On the west, there is opportunities for hydrogen, no question, but perhaps not as much with nuclear hydrogen. It's
Thank
Colombia.
you. Yeah, thank you so much. I think I could dive into that for a while longer, but we need to move on to our next and final speaker. For that, we go to Europe and hear what's going on in France from Dr. Jean-Michel Rougerie, who has been at the French Alternative Energies and Atomic Energy Commission, or CEA, since 2000. He previously headed the Neutronics, Nuclear Physics, and Severe Accidents Research Laboratories and the Innovative Systems Studies Service in Cadarache. Since 2019, he has been the manager of the Small Modular Reactor Program of the Energy Programs Direction. Jean-Michel's presentation will cover CEA's vision for an integrated energy system to achieve a net zero agenda by 2050. This vision, which would utilize a mix of nuclear and renewable energy, would leverage small modular reactors to produce both hydrogen and synthetic or e-fuel production. Jean-Michel, over to you.
Okay, thank you, Shannon, for introduction. I would like to thank also the organization for the very good organization of this webinar, and also for the invitation to be at this meeting, at this webinar invitation. Okay, before going into the presentation, I would like to say that R&D on low carbon energy mix at CEA has been launched 4 years ago in the context of global warming issues, in the context of a new roadmap on energy in France also, and also in the context of 2050 net zero agenda in Europe. So when you know that context, and you know also that CEA is a RTO research technology organization that aims to help French government to have the policy on energy, it forces us to have this reflection to understand what will be the next low carbon mix in France and in Europe. So for that, go to the next slide. We develop at CEA a vision on integrated energy vision to achieve this 2050 net zero agenda. I will not go into detail, because not only because it's in French in the scheme, but just to let you understand that this vision on the integrated energy that mix together renewable and nuclear energy is based on 4 principles. The first one is the multi-scale principle, and you can see on the top the global, let's say, power plants and the global energy providing to continental scale. Sorry, and on the top, on the bottom, you will see a very small local grid and territorial assessment for the energy. And the second pillar is based on this small grids that needs to be seen as with smart grid issues that has been to be taken into account to have more renewable together with nuclear. The third pillar of this vision is on multi-vector issues, and that's where we can see that we do not look only at electricity, but we also look at it as vector, and gas like hydrogen, and hydrogen is one of the main issues that we will have to assess in this vision. And the last pillar, and not the last one, is on circular economy, and we would like to use also resources like carbon, CO2, because we also think that we need to go to e-fuel generation. This vision needs implementation on technical innovation, convergence between nuclear and renewable, and also business model and regulation, and also society approbation. Next slide, please. Next. Okay, thank you. No, the slide before. Okay, how could nuclear energy contribute to this vision? The first thing is that we do think that we need to have to achieve convergence between nuclear and renewable, and for that we need at the power plants, the big power plant scale, we need to have a flexible nuclear. This is the first things to match with variable renewable production that will be increased in France. The second thing is we do think that we need to have this SMR or AMR in local energy hub to provide local energy, power, and also not only power, but also hydrogen or heat or desalination in this local hub. The third thing is hydrogen production, and for that at CEA we also work on development of this high temperature electrolyzer, and we have also a joint venture on that field, but I would not speak about that in this presentation. And the last thing is the nuclear refinery that we would like to propose to be able to develop this, to have the production of e-fuel and e-carbon molecules. Next slide. So in this strategy, we say that we think that SMR is very important issue, and that's why we are working on this part to achieve this vision. SMR has to be seen as an integrating nuclear energy into territorial energy hub. We all know that SMR has to, the challenge of SMR is to achieve, to answer to several challenges, like a power grid that cannot be suitable for large nuclear capacity, provision for power to isolate sites, or decarbonization by replacement of coal power plants. But not only for electricity, we think that SMR are opening new issues, cases for nuclear energy, for process heats for energy intensive industry, for district heating also, and also for local hydrogen production and territorial use. That's why CEA is focusing on SMR and hybrid system for coupled to develop coupled nuclear system. Next slide. So this development of SMR is based on two pillars. The first one is development of SMR Newards. It's the French SMR to be developed for the next decade. The project is to have the deployment by 2030. And the main interesting thing is we do want to have this development with a multi-purpose by design to assess the heat cogeneration and especially also hydrogen production. And it gives you what is the time scale for us, the schedule to develop this hydrogen production with massive nuclear power plants with this SMR. Next slide. The second pillar is based on what is the R&D that we have to propose to develop this SMR bioelectricity initiative. And the name of this R&D that we have launched at CEA 2 years ago is Innovative Decarbonized Nuclear Energy System. And you can see the system in the middle of the scheme. And we would like to assess this type of system that can provide together with electricity, heat for high temperature electrolyzer, heat for district heating of industry. And this can be made only by studying the multi-vector energy conversion system. That is one of the R&D part that we have. It's the fourth part of the R&D on innovative energy conversion system. The second thing is to achieve and to have an assessment of the market of hydrogen and heat, because if we do not reach the market, we don't have to develop this type of SMR, hybrid SMR. And the second, together with these two first, let's say, pillar of this R&D, we have launched the studies of two type of use case. Let's say the first one is SMR dedicated to heat in cogeneration to provide only let's say the top part of the scheme, heat and electricity for district heating. And the second studies that has been launched is a use case on SMR dedicated only to hydrogen production with high temperature electrolyzer. And we have studies this hybrid system to understand what can we do with 10 to 20% of heat cogeneration with PWR type SMR. Next slide, please. Okay, this was only to give you let's say, an example of what can be the achievement of the coupling of an SMR of 450 megawatt thermal with a high temperature electrolyzer. It can give you 100 ton per day of hydrogen. It gives you an idea of what is the size, and we are working on this coupling of this solid oxide cell that we are developing in CEA for this to achieve this type of development of hydrogen. Next slide, please. So, as you know, in France, we also are involved in the European strategy on net zero agenda, and we also have launched a European project. The name is Tandem, and this project aims to identification of hybrid system for hydrogen and heat. And at the end, the project of 3 years project will aim to have a recommendation to stakeholders and also to policymakers to know how to develop this nuclear SMR nuclear development for hydrogen and heat. And the last slide is the last stage of the rocket. Is what can we do with nuclear and hydrogen and electricity and heat? And the last thing is we do think that we need to develop this nuclear refinery for e-fuel and e-carbon molecule. And that's why we are focusing our development on the building technological brick for that, and developing also program together to reach this type of nuclear refinery. And that was my last slide. Just to conclude, I can say that we have the same problem to solve, and that's global warming, decarbonization of energy, etc. And what is amazing is to see the six presentation that we have today. We almost reached the same R&D to be developed, the same vision. With okay, we have to have a mix between renewable and nuclear, and it's very interesting. And also, what is amazing is that this vision that was quite useful for our French government, because they launched two roadmap, one on hydrogen and one on nuclear for France 2030. So it's quite interesting to have done this study and to go ahead on that. Thank you.
Thank you, Jean-Michel. I think you're quite right. We've got a global challenge in front of us with regard to climate change and reducing emissions. And while it shouldn't be surprising that we're all starting to convene around similar solutions on nuclear and renewables and hydrogen and decarbonizing industry, it is refreshing to see that we're converging and perhaps have some opportunities for data sharing, experience sharing to really accelerate this progress. So my first question to you is, CEA seems to be focusing on small modular reactor solutions, light water reactor solutions. Why are you not pursuing some of the high temperature reactor options that are being developed to couple with high temperature electrolysis?
Oh, there is two issues on that. The first one is that we would like to achieve that in the next, let's say, in the next decade. So we do think that we need to have the first coupling of electrolyzer, high temperature electrolyzer with SMR on PWR type, because it's let's say on the schedule together with what we are developing on the high temperature electrolyzer, and also on what we are developing on the new world SMR. And the second thing is a completely technological explanation, is that we on the system that we are developing, we only need to have a steam at 150 degrees, so it's just fit with PWR type SMR, so it can be. And then after that, I think that we assume that we can use that when we will develop advanced modular reactor, perhaps in the future. We can use this development to couple it with higher temperature reactor.
Mm-hmm. Well, we're doing much the same in our initial pursuits, utilizing light water reactor technologies to support high temperature electrolysis. And I think it helps us to dispel this myth, this preliminary thinking that we need a high temperature reactor to drive high temperature processes. In fact, there are many approaches to heat augmentation when we do need to couple at higher temperatures. And it's both near-term solutions with technologies that we know well, and then later solutions that might provide higher efficiencies. So thinking about some of these deployment opportunities, what do you think is a reasonable schedule for deployment of these types of integrated systems?
Yes, it's related of what I have just said just before. We said, okay, we need to develop the first brick of technology like high temperature electrolyzer, like SMR to be developed also. And we know that the first part of the roadmap is to 2030 to 2040, and then after that, we will have a second deployment for carbon capture, big facility together with combining molecules to combining CO2 with hydrogen, and we see that perhaps after 2040, and it's just a roadmap that have to be developed together with all this brick. That's why we try to have this vision at 2050. It's an integrated vision, but in the between, we have to develop all the brick and the systems one after all.
Well, thank you so much for those remarks. I think that there are many solutions, including different reactor technologies, different hydrogen production technologies, different integration approaches, and it will take all of them to achieve some of the goals that each of our countries and organizations has set out before us. We are running up close to time, so I want to thank everyone for these excellent presentations and the discussions. I wish we had more time. There's certainly many questions we did not get to, and certainly won't in just 2 hours, because there's so much work going on and so many opportunities coming forth, and many countries that we weren't able to reach to within this webinar today. But hopefully we will be able to engage in future webinars. So at this point, I'd like to give the last couple of minutes to my DOE colleague, John Michael Murray, to offer some closing remarks.
Thank you very much, Shannon. Thank you especially for your wonderful moderation, and a big thank you to all of the panelists as well. This has been a very illuminating discussion with excellent speakers. Clearly, these are very exciting and promising technologies, and we hope that this webinar has spurred greater interest in them, as well as inspired further action in the clean energy sector. Again, please visit our website and join NICE Futures efforts as we prepare for the 13th Clean Energy Ministerial being held in Pittsburgh from September 21st to the 23rd. Again, thank you very much and goodbye.